The better you understand sedimentary rocks, the better you will be able to interpret the environments of the past and the conditions that were acting on the grains that were laid in place. We classify sedimentary rocks into two categories based on their genesis. The first is detrital. So these are the physical detritus that was beaten and pulverized and mashed up. And then it was pushed down, it was transported by some sort of agent. And then when that agent lost its energy, these grains were left behind. Whether these grains were anything, it's like the great size of a grain of sand all the way to a massive, massive boulder. The other types of sedimentary rocks are non-detrital sedimentary rocks. So these are the chemical rocks. They are made by either organisms, their shells, their exo and endoskeletons, their poop, or the precipitation of crystals. Indeed, some sedimentary rocks we find crystals growing inside, like geodes, and these are forming from chemical means. The groundwater or the ocean water, the lake water, has ions in solution, and these solutions start to crystallize and they fall out, much like your alum crystals in your water. So of these two, everything is transported. And what are the transport mechanisms? Well, the first is ice, but in ice, usually the grain sizes that we find are mostly just clays and then large grains, because ice as it moves can pluck off massive boulders and cobbles and gravels from the valley walls and the valley floor, but the pressure of the ice pushing against these grains and pushing against the valley floor pulverizes them into a powder on their outer sides. And so we often find large grains smothered in a veneer of clay grains, a powder of their own selves. And then wind. Wind is very feeble. It can't transport anything greater than a sand grain. And even when you get down to the finer particles of clay grains, like shale-like grains, these grains are so fine that oftentimes the wind just keeps carrying them and keeps carrying them, and they never get deposited. Iceland is still battling with the 2011 eruption of Eyjafjallajökull 2.5 years later, because the ash is about the size of a clay grain, and so it's still suspended in the air and it's just not depositing. There are some sand dunes like out in the Sahara and here in the past in North America that had massive dust storms, and these dust storms brought vast stores of clay grains that just lingered in the air and were able to thinly deposit in very tiny thin beds that are maybe only a couple millimeters thick, and they do great things to control the features of landforms that we find today, such as standing lone rocks and little caves. The last transport mechanism is water, something that makes caves. Water is the commonmost agent because anywhere on Earth it can flow. It can transport any grain size because it is, well, it's a medium that has lots of energy. It's a much thicker, much more solid material than wind. Wind is just fine little gas, and it's very difficult for gas to support anything larger than a sand grain. But water, tumbling H2O, can carry any grain size based on its velocity. And the function of velocity is what we call its bed load. So bed load is defined as the lightest mass transported along the bed. So if ever you've stared at a stream and you've watched sand just kind of creep along the bed, like at the forefront of what might look like a little dune slope, and it just tumbles down and it just progresses, this is bed load. This is what's being transported and pushed along the bed. And as soon as the energy of that system drops, the bed load becomes what is deposited. So as the bed load continues to be pushed, it's not being deposited. We need energy to drop in order for bed load to become part of the rock. So if we're looking at sandstone, then sand is being deposited, so the bed load would have to be something like silt or clay, something finer. If we see in rock that cobbles are being laid down, well, if cobbles are being laid down, that means that the water can still carry gravels. And so gravels are being pushed along the bottom of the stream bed, but only cobbles are really falling out to become part of the rock. This reflection tells us that grains indicate environments and the energy in their environment. So as you hold a rock, this seemingly dead and lifeless thing, this thing that has a certain color, take a look at its grains. Look at the roundness, the sorting of the grains, which we'll get into how to do. But connect to these things and ask yourself, where can I find this? You can't really do this with an igneous rock. You can't really do this with a metamorphic rock. But with a sedimentary rock, you can connect to it because it happened on the surface of the earth somewhere at some time. So here are the grain sizes. You'll be getting a grain size folder that helps to break down these sizes as well. And because the size in millimeters is often lost on us, I've given you food because, well, food is awesome. Everybody knows how big a pea is or how big an apricot is, and it's much more easily relatable. But if ever you're out in the field and you just want to measure these things, you can do that as well. You can do it the boring way, or you can bring some tabbouleh and mashed potatoes. Yeah, and then the energy that we see on the right-hand side, these are the energies that are required for the grains to be deposited. So cobbles take a high energy in order to be deposited, meaning they will be tumbled along and carried in the medium, in the transport mechanism, under a very high energy, but they'll settle in a high. Sand settles in a moderate to low energy, depending on the sand size, because as you can see, sand has a range in sizes. And then clay, something that feels, it's more like a kind of a stiff pudding. It's like a very thick, viscous pudding. Most clay won't settle unless there's no energy whatsoever. So, as I've mentioned before, the environment imparts distinctive characteristics to accumulating sediment. Well, let's see some examples then, you should say. First, in cold, deep, salty water. So out here in this like deep marine environment, this is the location where finally the precipitation of calcite occurs. And it occurs just as your alum started to grow as little crystals in the water, but because they are more dense than the water surrounding them, they kind of do, in igneous rocks, fractional crystallization. They fractionate out. They remove themselves from the solution, and they will start to accumulate down here at the bottom. And this accumulation will just build and build and build to balance out the solution of the water. In lakes, although you might say, hey, cool, seasonal clays. Well, there are carbonate clays and then there are non-carbonate clays. Because these carbonate clays down here are forming from precipitation. They are a chemical rock, whereas lake clays are forming from the powder that is occurring upstream. So seasonal clay layers are often occurring because the water that is bringing in clay is bringing it at a much higher rate during the spring and summer of the spring and summer thaw. There's a huge influx of clay, so the water's usually dirtier, more nutrient rich, and then it settles out. But if we were to track the clay accumulation over a year, we would see that the accumulation is greatest in the spring, starts to slow in the summer, and the clay usually here goes from like a gray to a brown, and then in the fall and the winter, the clay stops accumulating so thickly and becomes this thinner, very dark, usually black line. And it's usually littered with the bugs that died in the fall and the winter. And so this change from thick gray and then gradationally changing into thin black is a lot like a tree ring. Indeed, there are many scientists that go out to lakes, core these things, count the variations just like tree rings to figure out how old the lake is and how long ago these bugs lasted, because bugs are very sensitive to climatological changes. And by understanding the populations of bugs, you can, within about 2 degrees Celsius, say what the temperature was of that lake at a given time. This is a great way to study climate. Beaches. Beaches with the wave action, just the waves just crashing in, allow for these sand grains to float and lightly impact and just start to round each other out. They remain glassy in their color and in their outside because the water acts as bit as a buffer, and they're just rounded out slowly and steadily under the pressure of these waves and these small little particle collisions. Whereas on a sand dune, the only thing you have are particle-particle collisions, grains pounding and banging into each other, creating pocks and pits, fractures. And so sand dune sand is rarely anything other than subrounded and frosted because the thing has been sandblasted. And then, new word, turbidity current. A turbidity current is, well, it's turbid. The grains that are moving and flowing along are constantly turning over, constantly roiling and rumbling. And turbidity currents usually occur in a submarine canyon or even in an aerial canyon where the wall just topples off, starts to tumble down the canyon and create something of like a submarine fan, a giant debris flow or an avalanche flow. And this avalanche flow has very high energy, but then it starts to lose it immediately. And as it loses it immediately, all sorts of grains are falling out, such that it finds upward. At the bottom, we have conglomerates of cobbles and boulders, and then quickly we see no cobbles and boulders, but instead gravels and pebbles, and then at the very top we see muds, we see shales. It is high energy, it's a sudden stop, but the setting is gradational enough to allow us to see this change from boulders, cobbles, gravels, pebbles, sands, silts, clays. That needs to be a wrap. I challenge you, make a wrap out of that, out of grain sizes. That'd be cool. So there are two other characteristics we can talk about, especially when we get into defining rocks as conglomerate and shale. And the first one is rounding. Do you have sharp corners, or have they been knocked off by the attack of collisions and chemical weathering? And then there is sorting. What's the size variety? Is there just one size, so it's well sorted, or are there many different sizes? Are the different sizes, very close together in their grain relationships, like pebbles and gravels, or is it totally extreme, like silts and boulders? What's the sorting? The sorting tells you everything about energy type. For instance, well sorted, so when you go to a beach and you find just sand grains, that's well sorted because the energy type there is sustained, because the energy changes were very gradational. If you were to follow upstream where these grains were coming from, you would gradually see an increase of grain size away from the beach. Whereas if you were to go under the water, along the bottom, you would see a gradational change from sands into silts and then into clays. So of these two, which is which? What's their rounding? Sub-rounding, angular, well-rounded, and what's their sorting? Well, on the left, first we have, they're well-rounded, but they're poorly sorted. Gravels, pebbles, and I even might see cobble. Whereas over here on the right hand side, these are very angular. They have sharp corners, sharp edges. They are not at all rounded, so they haven't really had a whole lot of collisions, haven't had a whole lot of chemical attack, probably haven't been exposed for a very long time. They're probably very near the source from which they came. So what else is a rock? How do you make it? How do you get these grains into making a rock? Well, thankfully, there's just two steps. Step one, got to compact the thing. Compaction happens by burial and packing the particles into a smaller space, so volume reduction. And then step two, you got to cement it. So with just compaction, even intense compaction, you get something like the ash that you have, the ash rocks. That's compaction. That's not real cementation. It's just moderately consolidated. But once you cement it with precipitated ions like quartz, calcite, and iron oxide, those are the three primary ones. Around here in Colorado, we just have quartz and iron oxide. But the precipitation of these ions from groundwater in between the spaces of these grains is what really holds them together. And so based on how much cement, is it well cemented, poorly cemented, tells you just oodles about the rock. This all equals lithification. So just compaction, cementation, that's all you need. To mind map this out for you, let's first go through mechanical weathering. So we'll be over here. So we break up these rocks, boom, boom, bam. We've got gravel, sand, silts, and clay-sized particles. So physical things you can throw them in your mouth, you can feel them with between your fingers. Okay, great. They're transported. They fall out because of energy is reduced. They can't be carried anymore. Then they're lithified. You get a detrital sedimentary rock. So physical things, totally, you can feel them, stick them in your mouth. Children eat them, babies eat them, and we say, no, don't do that, but they do it anyway. These things are detrital sedimentary rocks. Now, if in that child's stomach or out here in nature, we chemically break these things up and we get ions and compounds in solution, these things are going to be a chemical rock. Because if that child chemically wears that pebble by an organism, because they are an organism, and they poop it out, they have just now deposited, and this thing will become a chemical set. Yes, poop, if it were to be solidified, would be technically a chemical sedimentary rock, as weird as it is, but that is the truth. If we chemically weather things into blocks like sands, silts, gravels, clay-sized particles, if we have not put these in solution, but we have physical things, even though we chemically broke them up by something like hydrolysis, so that's water destructing and ripping apart things, hydration, just saturating things with water, dissolution or oxidation, if we end up just dissolving something that separates a gravel, separates a sand, a silt, or a clay-sized particle, that will still have to be a detrital sedimentary rock. The way you get chemical rocks is by having ions and compounds in solution and then getting gobbled up or precipitated out and then deposited. That's the difference. And again, to just remind you, the three mechanical agents that we use and we respect are wind, water, and ice. Some people say gravity. I say no, because wind still blows, water still flows, and ice pushes things off ledges. These are usually what's really causing these rocks to fall down. So what do you analyze? When you look at a rock, what should you be looking for? There are 5 things that I want you to always look for. The first are the grains. These are the large clasts, the large clast that you see. Oftentimes you'll be looking at a rock and you'll only see one clast, one certain grain size type. There, that's the grains. If, however, say you have pebbles and mud, or cobbles and clay, cobbles and sand, if the grain sizes are extremely different, okay, and you've got a poorly sorted rock, then you not only have grains, but you have now matrix, something filling in the interstices that is not cement. I'll say that again. Matrix are grains that fill in the pore spaces that are not cement. If they are grains, they are not cement, and they have a totally different function and are screaming at you a totally different story. So grains are the large clasts, matrix are the smaller grains, and the cement, this is the chemical precipitation that is just kind of growing in between the grains. They often encompass all the grains, but they don't have to. And if every single space isn't filled, then you have pores. You won't always have pores, but you'll definitely have grains. Won't always have matrix, but you'll definitely have cement. And pores, they are not only just trapped atmosphere, and so can be used to analyze the atmosphere of the past. They also tell us, what is the rock good for? Is it good for holding oil? Is it good for holding water? Can it hold gas? Will it let these things escape, or will things like limestone, which don't have pore space whatsoever, will they hold in the oil, the water, and the gas below them? And then lastly, the 5th thing is support. If you have grains and matrix, it's very important to distinguish whether you have grain-supported rocks or matrix-supported rocks. In grain-supported rocks, the grains actually touch each other, and then the matrix just fills in the small space between. This tells you that the energy changed slowly in the system. So the energy was carrying both sands and both larger grains, and everything's kind of tumbling down, and then as the energy gently starts to fall out, the large clasts can fall out and gather at the very bottom, and they can build up and build up with spaces in between, and then as the energy lowers and lowers even more, then the smaller grains can fill in the spaces, and then everybody is put to bed, and that's the end. for matrix supported, kind of what we see here, this is screaming that all hell just broke loose. This means that the very large grains are floating and tumbling all throughout this whole entire medium. They're at the top, they're at the bottom. It's totally mixed because this is a torrent. This is like the turbidity current at the beginning. Everything is insanely swishing around and changing position. You could have entire boulders the sizes of houses free floating in this medium, tumbling down, and these giant boulders will never touch the very base of this channel because this flow is just massive and has a ton of energy. The energy was created abruptly, almost geologically instantaneously, and then bam, instantaneously it stopped. So oftentimes we find matrix supported rocks as debris avalanches, volcanic debris avalanches, volcanic landslides, massive rock falls, whereas the grain support is usually something much calmer, something like a stream or a river that is constantly increasing in seasonal surges during spring floods, but nothing violent. So quiz, just to make sure you're on the right path with what you're supposed to be paying attention to. Take a look at these questions, pause, come up with a few answers, and come back. Otherwise, it's gonna feel really, really weird. So pause now, come up with a few answers. Okay, and we're back. See, if you didn't pause it, that definitely probably was really weird and startling. So the differentiations between these were found back, I think, on the second slide or the third slide, something, whatever it was about transport mechanisms. Ice, the grain characteristics will usually be clay and then very larger grains, but these larger grains will also often be angular and poorly sorted. Wind, remember this can only transport sand and silt, and clays are, although it can transport it, clays are rarely deposited because they're just so fine, they stay suspended for a very long time. And then water, kind of like ice, you can have sand to cobble, so mix of grains, and you can have, poorly sorted grains, okay. However, these will usually be rounded, and you'll have many other indicators to help you figure out that this was water and not ice. So what causes chemical rocks? Again, pause this. No, seriously, did you pause it? You did? You sure? You wouldn't lie to me. Yeah, you would sometimes. Jeez. Okay, so chemical rocks are caused mostly by some sort of form of precipitation, even if it's in the organism. We precipitate to make our bones even, but it's just facilitated through an organic process. And this organic process involves temperature changes, pressure changes, and pH. And then take this third question, write this down, think about it. It'll be a topic of discussion in the future classes. And then also answer these two and post these to the website. As always, if you have any questions, write them down now so you can remember to ask them tomorrow in class or whenever next I see you. All right, see you in class.